Dear students, this is lecture number 4. This lecture is about the Monte Carlo algorithm. Monte Carlo algorithm is one of the most important algorithms that used in simulations in many applications. And it's like the basic and the easiest one as well. Monte Carlo is a classical simulation technique. In fact, Monte Carlo is only one particular application of an otherwise general method, which is applicable in both deterministic and probabilistic settings. At the heart of the Monte Carlo simulation is a computational procedure in which a performance measure is estimated using samples drawn randomly from a population with the appropriate statistical properties. The selection of samples, in turn, requires an appropriate random number generator, RNG, that we discussed previously. The term Monte Carlo method is generally used to refer to any simulation techniques related to the use of random numbers. This is a general term for Monte Carlo. If any algorithm that uses a random number in sampling, one way or another, it will lead to Monte Carlo method of simulation. The term Monte Carlo method is generally used to refer to any simulation technique related to the use of random numbers. This includes methods such as Monte Carlo simulation, Monte Carlo integration, importance sampling, genetic algorithms, simulating annealing, the Hastings metropolis algorithm, percolation, random walk, and ballistic disposition, just to name a few. These are some kinds of examples that use Monte Carlo simulation, or they are considered Monte Carlo simulation. Monte Carlo simulation generates random inputs in reference to a known distribution. We discussed about distribution. There are many kinds of distribution, and uses these inputs, to determine a numerical value of performance measure. So Monte Carlo simulation will result for an approximate value that we cannot conduct or compute in real world. Okay. The essential part of Monte Carlo simulation is a procedure for generating a pseudo-random number R that's distributed uniformly over the interval 0 and 1, as we discussed in LCGs, linear congressional random number generators, in the previous lectures. Such a procedure is applied repeatedly within the Monte Carlo simulation to produce a sequence of independently generated random numbers. There are three characteristics of Monte Carlo simulations. These three features common to all Monte Carlo simulations, which are they? Okay, the first one, a known distribution over the set of system inputs, random sampling of inputs based on this distribution, specified in feature 1, and simulation of the system under the selected inputs. The third one is the numerical aggregation, the method you calculate the total or the average number, or in other words, numerical aggregation of the experimental data collected from multiple simulations conducted according to feature 2, which is the random sampling. To make the results more accurate, we have to conduct or collect multiple simulations using random sampling. Okay. The Monte Carlo algorithm is based on so-called law of large numbers. Okay, we will discuss this later in the example. Why it's large numbers? Because if we are going to, if our problem has very big number of samples, and we cannot put all these samples on computer system or even in real world, we have to make random samples over evenly distributed among these samples, and make a suggestion that these samples are factor them or scale them to make to get the grasp of the original problem itself. This mathematical result of probability theory asserts that if one generates a large number n of samples such that x1, x2 to xn from a space x, and compute a function of each of the samples, f of x1, f of x2 to f of xn, then the mean, the average of these values will approximate the mean value of f in general on the set X. That is, as n tends to approach to X, we see that the following holds. Okay. Here, n is the number of samples to the set of X. Okay, the rule is very simple. We collect the functions of each sample, then we will take the average, the aggregation function or average of them, and we approximate this as like we will follow a general rule that the output of such sample will be the function star, which is approximate value for the all functions, for the all samples. Okay, we will understand this algorithm more in the example. Okay, to make it simpler, a toy example is that's very basic example of Monte Carlo simulation. It's usually used for in estimating areas. Suppose this figure. Okay, we have this irregular shape. Say it what it's like. So it's a solid or it's liquid or anything else. Okay, we need to measure the area of this irregular shape. Okay, we have two things. If we just encounter or like limit these irregular shapes and a regular shape that we can calculate the area. For example, the area of a rectangle is its length multiplied by its width, which is in this case is like 10 by 4. The total area is 40. Okay, because it's regular shape. But how about the irregular shape? How we can measure or estimate the area of this irregular shape? One will say, okay, we may use like another liquid and add some few liters, and that if this is a pool or some container, but this is not a container. This is like say that how to measure like the area of ocean or something that's so big that you can't measure it. The way to do that is to use Monte Carlo simulation. Okay, our problem in this case is what's the area under the curve covered by the dark area. Okay. To further understand Monte Carlo simulation, let us example a simple problem. Okay. Below is a rectangle with which we know the length and height or width. It is split into two sections which are identified using different colors. What is the area covered by the dark area? Okay. The solution of this problem is easy. Due to the irregular way in which the rectangle is split, this problem is not easily solved using analytical methods. So, an analytical method we usually make an equation or take like if it's like it's not a second degree or third degree or fourth degree equation. This irregular shape has like infinite number of equations or analytical problem to solve, and this is impossible to do in real life. So instead, we are going to use random number simulation, which is mainly Monte Carlo simulation, to easily find the approximate answer. The procedure is as follows. Okay, randomly select the location within the rectangle. Say like select any location randomly. Say like we will have like 1000 sample or 100 sample. Here we took 10,000 sample because in computers it's easy to take very large numbers. Okay, if it is within the dark area, record this instance as a hit. Like we need to make two counters. If it's in white area, you will increase the white counter. If it's dark area, you will increase the dark counter. Okay. Generate a new location and repeat the steps for 10,000 times. Actually, in real simulation, computer simulation, 10,000 is a very small number. We usually use very large numbers to make accurate estimation or approximation for the answer. Okay. After using Monte Carlo simulation to test 10,000 random scenarios, we have now three things. Okay. The first thing is the whole area, which is known to us because it's a regular shape, rectangle. We have the samples, number of samples of white hits, and number of samples of dark hits. We will have a pretty good average of how often the randomly selected location falls within the dark area. We also know that the basic mathematics that the area of the rectangle is 40 square units linked by height, thus the dark area can now be calculated. The dark area will be equal number of hits to the number of samples, total samples taken. This, I mean by number of hits is number of hits of dark areas divided by the total number of scenarios or number of samples multiplied by the total area. I mean by this, like this is the almost the approximate ratio of the dark area. By dividing two samples, like number of dark samples to the total number, we are finding the ratio of the dark area, because we are using, don't forget, we are using random sampling. Like each time the sample is in different position. It's not like linear distribution or something else. Okay. So we could find easily how the approximate area of just multiplying the ratio of the dark area to the total 40 square units. So naturally, the number of random scenarios used in mathematical simulation does not have to be 10,000. If more scenarios are used, an even more accurate approximation for the dark area can be pointed. As we discussed previously, if we increase the cost of calculation, we will get more accurate approximation, depending on the problem. If the problem does not need our result to be so accurate, we don't have to make too many scenarios. We will suffice to small number or limited number, adequate number of samples to do the simulation or to get the result. Okay. The example of electric car battery charging station. Actually, this is from previous lecture, so skip this. Okay, we have the merits, the advantages and disadvantages of Monte Carlo simulation. We may call it like merits. Merit is like a good thing or something that give you excellent results, and drawbacks that like we may face problems or some difficulties in using Monte Carlo simulation. The main advantages of using Monte Carlo simulations are it provides approximate solution to many mathematical problems concerning systems that involve an element of randomness that can be modeled via distribution. It also provides a framework for statistical sampling of inputs, allowing results from numerical experiments to be aggregated in a meaningful way. Its use is quite simple and straightforward, as long as convergence can be guaranteed by the theory. For optimization problems, it is often can reach global optima and overcome local extrema. Okay, if we try to solve problems using analytical problems, mathematical methods, we may reach to local extrema or local minima. In this term, because we are using randomness in Monte Carlo simulation, we oftenly reach global optima, which is the best result we are going to find. So this are the main advantages of using Monte Carlo simulation. It's easy to use. It can avoid local minima or maxima or extrema. It provides a framework for statistical sampling that allowing results from numerical experiments to be aggregated in a meaningful way. It provides approximate solution to many mathematical problems. It's a general method. You can use it in almost every application. If you know the distribution of this problem, of course. One simple problem we can solve, usually scientists do, like if you take a picture of the sky in the night, you will see like many stars, like many stars, billions of stars. How to count them? What is the easiest way to count them? Okay, you can use like Monte Carlo simulation to count like number of bright pixels in captured picture of the sky, and you divide that with the total area of the sky in the picture, then you'll have approximate number of stars as well. This follows the same procedure for finding estimating areas. Okay. Although Monte Carlo simulation is very important and very useful, it has its own limitations. It was originally developed to study properties of stable systems that are inequilibrium systems, which the values of performance measures are not fluctuating. This is a step we have to think about. If the system is stable, it's okay to use Monte Carlo, but if not stable, it's not in an equilibrium position, which many problems has such fluctuation, which many current problems that are not stable are trying to solve. So we can't use Monte Carlo in unstable systems. It is not universally agreed whether this method can also be used to simulate a system that is not in equilibrium or in a transient state. That means sometimes systems are more transitional, like they change their states from one state to another state. So if you use Monte Carlo in the first state, you will get a result, but in a different state, you will get a different result. So it's very hard to use such simulation in transient state systems or systems not equilibrium. To use the Monte Carlo simulation, one needs to generate a large number of input samples, since before doing so, the law of large numbers need to be held. Okay. This can be time-consuming in practice if each simulation itself takes a long time. We discussed that generating large number of input samples, generating large numbers of random numbers, or we have to use the law of random numbers, which does not exist exactly. So there is no such rule that your distribution is random exactly. So as you know, random linear generators, this is different from one algorithm to another algorithm. So if you are going to use Monte Carlo simulation, very large scale of samples, your random number generator should be as good as your simulation. So you will spend too much time in generating such random numbers. The results of Monte Carlo simulation are only an approximation of the true values. You will not get exact results because you are taking samples of the system, not all the system. This is one limitation. When the performance measure has a high variance, the values produced by Monte Carlo simulation will converge to mean value over X. But any given sample from X may vary greatly from the computed mean. Okay, so we all know what is variance. Variance that we like when the samples are very diverse, like very different from each other. So we have very high variance. When we have very high variance, it is difficult to find the mean because Monte Carlo simulation computes the mean value, the aggregate, the average value. With the samples with high variance, it is difficult to get exact mean value unless if you use like very large number of samples to get to reach your computed mean. This is another limitation. The distribution over the set of inputs must be known in order to sample from X. If you don't know the distribution, so you can't use Monte Carlo simulation.